In this chapter, we're going to be talking a lot about the structure of molecules. Now, last chapter, we were talking about the structure of atoms and atomic orbitals and where you're going to find specific electrons within those orbitals. But now we're going to take all of that a step further and talk about how these atomic orbitals start interacting with each other so that they can bond together and actually form molecules. The first video that I linked you to did a really good job of outlining the energy considerations of some of these orbitals. And he pointed out that atomic orbitals, the s, the p, the d, and the f, he pointed out that s and p orbitals are different in energies, which is really something that we also talked about too. But what happens is that you start out with atomic orbitals in atoms, in neutral atoms, and you're also going to find them in ions. Now, you'll recall from your first year chemistry class that there are times when atoms will either gain electrons or they will lose electrons from another atom. And then, like for example, in table salt, chlorine will gain an electron from a sodium atom, and then the electric charges of those will attract each other to form an ionic solid. It's not a sharing of electrons, it's a transfer of electrons. So that's in an ionic bond. Everything that we're talking about in this module is going to be a covalent bond, a sharing of electrons. But you're going to find atomic orbitals in either neutral atoms or in ions. And so this is the S, the P, the D, and the F that we talked about in the last chapter. Now, in order for these to be able to bond together most expeditiously, they're going to combine together in what we're calling a hybrid orbital. Now, if you think about a hybrid, you think of, you may remember hybridization from when we talked about biology, where you put together a purebred of one thing and a purebred of another thing, and you mix them and you end up with a hybrid. This is very similar to that. We're going to mix atomic orbitals together. It's kind of like putting them in some sort of a blender. And these hybrid orbitals are really just an intermediary state. It's really a model to help us understand what's going on down at the atomic level. And so then this intermediate state, these hybrid orbitals, will then overlap with one another to form molecular orbitals. Atomic orbitals and hybrid orbitals are focused around just one atom. And in order for molecules to form, they have to share the electrons. In order to share the electrons, they have to be able to orbit both nuclei of the atoms that are sharing those electrons. So a molecular orbital is where you can find an electron orbiting in around both nuclei that are actually sharing that electron. So atomic orbitals and molecular orbitals, the hybrid orbitals that we're going to spend a lot of time talking about are kind of an intermediary state, but they exist so that they can form these molecular orbitals. Okay, so I've got a table up here on the board, and this hopefully will relate to some of the things that we learned last year as far as molecular geometry. Now, he does not talk in the book a lot about bond angles, but we are going to talk a lot about bond angles. And some of the assignments that I'm going to be giving you are going to be focusing quite a bit on bond angles. So even though he doesn't mention it much in the book, you do need to be aware that I do expect you to understand the effects of some of the different things that we're going to be talking about, especially lone electron pairs, the effects on these bond angles. That will become clear in the coming days with some of the assignments that you're going to be doing. So the table that I have here, this column is going to list the atomic orbitals that are going to combine together. We're going to put them in the blender, and we're going to spit out a hybrid orbital. So if I recall that you have, in each energy level, you have one S and you have 3 p orbitals, all oriented at a different direction, one along the x-axis, one along the y-axis, one along the z-axis. Okay, so if I take an s orbital and one p orbital, put them in the blender, mix them up, I end up with an sp hybrid orbital that has a completely different shape. The s orbital has a lower energy than the p orbital does, but when I make hybrid orbitals out of them, they now are going to have the same energy. Okay, the sp orbitals, if you have a molecule that's made out of sp orbitals, that is going to have a linear shape, and it's going to have a bond angle of 180 degrees. So that means they're going to be, sticking out straight from each other. Okay, if I take an S and 2 of the p orbitals, and I put them together, I will end up with sp2 hybrid orbitals. And the sp2 hybrid orbitals are what are going to make the trigonal shape, and it's in a plane. And so the farthest apart that you can get 3 things in a plane is 120 degrees. Again, you've got pictures of these things in your book, and the other videos that I linked you to are going to help point that out as well. I just trying to combine all of it in a table so that you can see all of it at once. Okay. Then if I combine an s plus 3 p orbitals together, the x, the y, and the z, I end up with sp3 hybrid orbitals. And that's going to make the tetrahedral shape where you've got kind of 3 down on the bottom and 1 kind of sticking out up at the top, but they're all of those are all the same distance apart. They're all 109.5 degree bond angles there. Okay. Now, it's also possible, and this is something we'll get into a little bit later in the chapter, but he does start to talk about it here. We'll go into more detail a little bit later, but we can actually have d orbitals that will get into this mix of hybridization as well. So if I have an s and 3 p's and a d, the name of the hybrid orbital is an sp3d orbital. And what that looks like is a trigonal bipyramid. Now, the picture I drew here, I'm actually going to try to draw it up here so I can make it a little bit bigger so you can see it. If you have a central atom here, then you've got one that comes straight up and one that comes straight down like this. And then the other 3 pieces of that, you've got one that sticks out this way. You've got one that's going to stick out kind of in front of the blackboard here, or the dry erase board, and you're going to have another one that goes behind the dry erase board. So this middle section of it really is the same thing as the trigonal shape, because these guys right here are all 120 degrees apart. But then, because this is sticking straight up and straight down, the distance between this one and this one, these have bond angles of 90 degrees, okay? So hopefully with that being a little bit bigger, you can see what I was trying to draw down there. And then finally, if you take an s and 3 p orbitals and 2 of the d orbitals, then you end up with sp3d2, which then will give you an octahedral shape, and all of those are 90 degrees apart. And so if I would draw that, it would look sort of like this. I'd have one straight up, I'd have one straight down. I would have 2 sticking out in front of the board, and I'm going to have 2 sticking out behind the board, and they're all going to be flat. So it's like this plane is cutting through the center of the board this way. And so everything here, all of those are all 90 degrees apart. So again, the thing to remember here is that these atomic orbitals, these guys are all different energies, but then when I hybridize them and put them together, these are all the same energies, and that's part of the purpose of hybridizing them. Okay, so introduction to hybrid orbitals, and we will get much deeper into this as we move through the module.